Welcome to this analysis of some of the data from the Ohio 2020 general election. The reason I put this video together is to discuss some specific allegations made by a friend of mine. He believes that if you do an analysis by voter age of the county level voting patterns for the 2020 general in Ohio, there's indications of fraud. I think my friend is wrong, and I want to share with you why I think he's wrong and give you some tools to help you consider his specific allegations. So I'm going to introduce myself in a moment. I'm going to present my friend's analysis as fairly as I can, and then explain to you why his analysis works. And it actually works well. I'll explain to you why it works well, but why his results don't indicate fraud. I'm going to hit a couple of his other talking points along the way. My focus is going to be on the data and the analysis. I don't really want to talk about people. I don't want to talk about motives. I don't want to talk about who might be the better president or anything like that. This is strictly about the data and the trends in the data. So first of all, who's involved here? First of all, I'm not going to name my friend by name. If you're watching this, you probably know who he is. He is a smart guy. He is well educated. He presents himself as a doctor, and he does have an earned doctorate in chemistry. And I've had a very long-term working relationship with him, not in a technical role, but I do know that he loves to work with data, so I'm not surprised to see that he moved into an analysis something like this. My name is Steve Teal. I have a doctorate in chemical engineering from the University of Texas at Austin. I am a licensed professional engineer in the state of Ohio, although I'm not presenting this in that capacity. I am currently on the chemical engineering faculty at an R1 research university in the Midwest U.S. My current research is on undergraduate education, not on research. I spent some time in industry, about 10 years, and during that time I earned a Six Sigma black belt. That's significant here only because that gives me a little bit more statistical background than most of the people you're going to see on YouTube talking about statistics. I'm not going to name my current or past employers because this presentation is strictly my opinion. It's not that of my current or my past employers. I do want to spend a moment, though, and just point out that my friend and I have similar publication records in the scientific literature. If you use metrics like the number of papers, number of citations, we both have an H index of 16 if you don't count self-citations. I am still research active and still publishing in the peer-reviewed scientific literature. And as I mentioned, I do have Six Sigma training, which puts a big emphasis on the practical use of statistics. So let's start out talking about his model. The starting point in my friend's analysis is the election turnout data for each age group statewide. You can take these individual data points and fit a smooth curve to them. Each of these points here is basically the ratio of the number of people that age who voted statewide divided by the number of registered voters of that age. So, here you see the number, or the fraction of 25-year-olds who were eligible to vote that actually did. Here, the number of maybe 70 or 80-year-olds. You can fit all the data to this really nice curve. And I think a smooth function here does make some sense, right? The behavior of a 71-year-old isn't that different from the behavior of a 70-year-old, isn't that different from the behavior of a 69-year-old. So you would expect to see some sort of a smooth function if you plotted this out. My friend fit this data to a 6-degree polynomial. We'll talk more about that at the very end of this presentation. At this point, though, the important thing is that you can do the polynomial fit, and it works pretty nice. It's not a bad regression at all. Now, you can combine that statewide data with some county level data. And his starting point at the county level is the age distribution of the registered voters in that county. I'm showing you here data for Hamilton County, where I live. And what you see in this plot is the number of registered voters plotted versus their age on election day. And this is data I pulled from the Ohio election database. And I actually calculated the exact age of each person on election day so that I could get their age in years. What this analysis says basically is I can work with that first graph, the statewide turnout by age. I can combine it with what we see in that second graph, which is the registered voters in a given county by age. I can take the voter turnout overall in a county and the voter turnout overall at the state level, and I can estimate how many people of a given age voted in a particular county. That's a lot of words. Let's run some numbers that might make it a little clearer what's going on. So let's look at 30-year-olds in Hamilton County. On election day, there were 13,055 30-year-olds registered to vote. 7,480 of them voted. So let's use the method to try to estimate this from the other data. From that chart that I showed you earlier, 57.88% of the 30-year-olds registered in Ohio voted. There were 13,055 30-year-olds in Hamilton County. 73.09% of the voters in Hamilton County actually voted versus 74.55% of the registered voters in Ohio. What my friend's method does is takes this number of 30-year-olds registered in the state times the number of 30-year-olds in the county, and then corrects by the ratio of the county turnout to the state turnout. And he comes up with 7,408 estimated voters in Hamilton County who are 30 years old. This actually compares very well with the actual number of voters, 7,480. This is within 1% of the true number, the estimate. This works pretty well. Now, there's nothing magic or special about the voting habits of 30-year-olds versus people of other ages, so I could do this for voters of all ages in Hamilton County, Ohio. If I do that, I get a graph like this. What you see here is the number of voters at each age versus the voter age on election day. The symbols are the actual numbers of votes, and this dark curve here is the back calculated number of voters. So that number I just calculated in the previous slide is right here. And you can see that that actually matches very well with the symbol. This method seems to work at the county level. I'd like to take an aside to talk about another set of claims my friend makes. When you look at the graphs he presents, he always shows a graph showing the number of eligible voters, the number of registered voters, and the number of actual votes. I'm not showing the number of eligible voters because I don't think we have a good estimate of them. There was no census in 2019 that we can use to give us a true number of that. I don't know of a highly accurate way to factor out what portion of the estimated total population is eligible or not eligible to vote. So any estimate you have of the number of eligible voters is just that, an estimate. Now, we do know the number of registered voters, but that's going to tend to be biased high. And the reason for that is that people aren't automatically removed from the voter rolls when they move out of state. They are removed from the rolls if you move somewhere within the state because you just update your registration. But if you move from Ohio to some other state, unless you think to drop your voter registration, it's going to stay on the records for a certain number of election cycles. So the number of registered voters is going to tend to be biased high. The number of eligible voters, we don't really know. So I don't think you can draw any kind of reliable conclusion about the true fraction of eligible voters who are actually registered to vote. Another point that my friend makes is tied to how well the number of actual votes correlates with the number of registered voters. Remember that the number of actual voters you have is the number of registered voters times the turnout. And you remember that graph I showed you, the turnout, it's a nice smooth curve. So what you see here for Hamilton County, Ohio, this dotted curve is the number of votes. The solid curve is the number of registered voters. And you can see that they have kind of the same shape, right? There's a peak here around 50. There's a little peak here in the early 70s. And these pretty much mirror each other. Now, my friend says that this is obviously an indication that something's wrong, but remembering that the number of votes is actually just the number of voters times turnout, and that you have this very smooth function here, you should be surprised if it was anything other than this kind of matching of the general shape. So the number of actual voters, or the fact that the number of actual voters qualitatively tracks the number of registered voters, is certainly not an indication of fraud. So let's go back to my friend's more complex method here. So as I mentioned, my friend's method works. I've shown you previously the data for Hamilton County, and I just asserted that this worked well. But I think rather than just saying this looks good, we need an objective test. Typically in research, the way we'll do that is to put together something called a parity plot. And I'm showing you an example of that now. Basically what you're doing in a parity plot is plotting your estimate, your back calculated number, some people will call that a prediction, as a function of the true number, right? I know how many people of each age voted. Each of these points represents some age group within Hamilton County. Along this horizontal axis, the vertical axis is what I back calculate from that method that my friend proposed. Now, if I had a perfect fit, if this method worked perfectly, the slope of this trend line would be 1, the intercept of the trend line would be 0, and the correlation coefficient would be 1. And here, r is the correlation coefficient. The square of the correlation coefficient is the fraction of the variance of the data set that the model explains. And I think these are actually the r's that my friend is talking about in his presentations. He never presents parity plots. He talks a lot about r's, and he presents a little bit atypically values of r instead of r squared, which is more usual. Keep in mind that r squared by itself doesn't tell you how good the model is. You also need a slope of 1 and an intercept of 0 if you're really trying to determine how well you can back calculate your data. So this approach, though, worked well for Hamilton County. Right, the slope of this line is 0.99 plus or minus 0.012. This is from a regression I did within Excel. The intercept is 47 plus or minus 70, so it's not different from 0. And the correlation coefficient squared is 0.997. So this is really good. The question that you should be asking now is this good luck? Did Steve just cherry pick a county where this worked well? Did Steve's friend just cherry pick a county that worked well? So I could do this analysis for every county in Ohio, all 80-some of them. That's really tedious, and I didn't really care to do that much work, so instead I did them all at once. And that what you see here is the parity plot for every county, for every age in the state of Ohio for the 2020 general election. So the slope of my parity plot here is 0.985, which is pretty good. The intercept is 11 plus or minus 2. That's pretty good. R squared is 0.998, which is really good. The question to ask at this point is, why is this correlation coefficient so high? My friend says it must be due to fraud because this is a really good correlation coefficient. But I think maybe we should be looking at simpler explanations before we go through some very massive, complicated scenario of election fraud. So to frame this, though, let's first think about how can you get high correlation coefficients? How do you get high R-squared values? Well, one way is if you have a really good regression model and really good data. Sometimes you can get those in instrument calibrations. You can get them in lab experiments if you've got really good control of your experimental conditions and really good analytical, if you have skilled people obtaining the data. So it is possible. My friend points out in the social sciences, very high R-squareds are kind of rare. And later on, I'm going to show you a way you cut this data set where that R-squared is going to look more like a typical social science correlation coefficient. Another way you can get a high R-squared value is you can cook the data. If you throw out all your bad data points, if you make up your data points, you can get a very high correlation coefficient. Another way you can get a very high correlation coefficient is to plot something against itself. Or more likely what's going to happen is you plot something that's proportional to itself or that's a linear function of itself. And it's easier to do that than you might think. So these are some of the ways that you can get high R-squared values. So let's turn to why this method works. And I'm going to give away my answer at the very beginning. It's not because there's widespread fraud. I am going to warn you that there is some math ahead. Hold on if you don't like math. I've done my best to simplify it as much as I can. But if you really want to understand how this works, you do need to do at least a little bit of algebra. The first question to ask is, what's the mathematical formula for my friend's method? So what he said was, if you look at the number of actual voters of age A in County C, you can calculate that based on the number of registered voters of that age in that county times the turnout of the voters of that age statewide, and then correct it based on the ratio of the turnout for the voters in the county to the turnout of voters statewide. And this TC and T are for all ages, not for that specific age. So that's how my friend's estimate works. When I've heard him talk about this, he's talked about this as using this product here, the number of registered voters times this age function is the initial estimate, and then putting a correction on it for turnout. I think another way to look at it that explains better why it works is to just use a little bit of algebra to say that you're estimating the number of voters of age A in the county by looking at the number of registered voters times the turnout in that county and then doing a correction based on age. But if that's the case, then we should be able to get a pretty good correlation if we just look at the number of voters of a given age in a given county as being proportional to the number of registered voters of that age in that county times the turnout in that county. So what happens if I do that? It actually works pretty well. This isn't a terribly pretty graph, but I'll point out that the correlation coefficient is about 0.97, which means this very simple model actually catches 97% of the variance in the sample. Very good. The slope you can see is close to 1. Remember, you need to look at both the slope and the intercept. Slope very close to 1, intercept essentially 0. This doesn't look like a very good correlation, maybe, if you've spent time looking at correlations. What I'll point out is that there's about 7,600 points in this graph, so a lot of the points are actually sitting right on top of each other in this lower region. And I'll also point out that the data span essentially 3 orders of magnitude, right? From hundreds to on the order of 10 to 12, 13,000. So you've got a huge spread of your data just based on the numbers of voters in each age demographic and a lot of data points. So that's going to tend to drive your correlation coefficient high. What happens if we now add the age correction? Well, if that's the case, then my correlation again goes to 0.998. This is the same graph you saw before. So you can see that what the age is doing is actually fine-tuning the estimate that you get based on the number of registered voters and the countywide turnout. Raises the correlation coefficient from about 96.7% to 99.8%, or you can put it in terms of the R. So another fair question to ask, since the claim is that they were basically trying to backfill to match this magic age curve, is how well does this actually back calculate the turnout of people of a given age at the county level? So remember, this top equation is the one we used to estimate the number of voters of age A in County C. I can also estimate the turnout of voters of A in County C by taking the turnout based on age times the turnout based on county divided by the statewide turnout. This is just algebra done on this previous equation. If I do that correlation, it doesn't look quite as good. Remember that we have this really nice polynomial fit to these statewide average numbers here, right? Very, very good correlation coefficient, 3 nines. I'll take that any day. If we instead look at the county level data, instead of taking the average statewide, I put all the county level averages, the chart doesn't look quite as pretty and the correlation drops to about 65%. which means that, yeah, lots of other things are influencing turnout besides age at any given age level. I'm not going to try even to dig into those because we don't know what those factors are. I don't have them in the database. But you can see that we have a lot of trending here. And these are also, by the way, count corrected, remember, for the overall county level turnout. If I put together a parity plot for this, this is the worst parity plot you're going to see in this presentation. The slope of the line is nowhere near 1. It's about 0.7. The intercept is nowhere near 0. Remember, this is on a percent or fractional basis, so about 25%. R squared is about 0.67. The county level turnout by age doesn't really match as well the state level turnout by age as you might guess it would based on the graphs showing total voter turnout. My takeaway from this is that the good correlation that you obtain is due principally to applying the county level turnout to the number of registered voters. That's the main thing that's driving this correlation. The age correlation, the age correction is far less important in this situation. We talked earlier about when you get high correlation coefficients. Well, I think what's happened is we're very, very close to plotting something against itself. We're looking at the number of voters by taking the number of registered voters times the turnout, but the turnout is just the ratio of the voters to the registered voters overall. So we're just very close to plotting something by itself. So what can we conclude from all this? First of all, my friend's algorithm for back calculating voting participation by age by county does work. Don't waste your time trying to prove this doesn't work, because it does. And as I've walked you through here, I think you should probably expect that it would. Parity plot results show that there's actually a great fit of back calculated voter participation with the actual voter participation. But this high correlation coefficient from the parity plots is due to using the actual number of registered voters in the county level turnout. The age dependence, that fancy polynomial curve, that's just a fine-tuning. I want to make another point about some of his arguments, and it's related to statistical methodology. If I recall correctly, my friend's first analysis like this was in Pennsylvania, maybe only a couple of counties in Pennsylvania. And he found this trend. He thought it looked fishy. And as I recall, the reason he started looking at Ohio was he wanted to use this as a control because his preferred candidate won in Ohio, so obviously it would be free of interference. When Ohio showed the same behavior as Pennsylvania, rather than rejecting his hypothesis, he rejected his control. And that's not how you're supposed to use controls. So I think he's made a major statistical misstep just in terms of how he's approached the idea of doing a control. Some final points. This method doesn't predict voter turnout. It back calculates it. People will sometimes call the model retrodiction or prediction. But technically, it's not a prediction, it's a back calculation. The parameter values that you use to do the back calculation are determined from descriptors of that total data set. So it's not like he's got some sample and he's using that to generalize what's happening. He's using the entire data set and basically back calculating elements of the data set from the whole data set. Another important point is if some value of the correlation coefficient is unbelievably close to 1, you need to establish some sort of a quantitative cutoff. How do you set an objective criterion before you do all this number crunching? You might remember that when I was talking about confidence intervals, I was talking about 95%, which is a fairly standard number. If you're going to reject some district's results, some county's results, based on a high value of R squared, you need to tell me before you do the analysis what R squared you'll accept. And even if this method were capable of detecting fraud, and I don't believe it is, it doesn't say who did it, right? So my friend said he saw exactly the same pattern, which he alleges to be fraud, in states where different candidates won the general election for president. This method doesn't give you an indicator of who would be manipulating the data, but then again, it doesn't prove that the data were manipulated. Let me close with some statistical stuff for those who care about statistical things. First of all, I used almost the entire Ohio voter registration database. There were some excluded records where the age appeared to be an error. If you actually do a deep dive into it, you'll find that there are a bunch of records where the birth date is January 1st, 1800. That looks like it's just a placeholder when they didn't have a valid birth date. That sometimes could happen if somebody doesn't have a birth certificate or something like that. So we don't know the ages of those voters. There were some voters whose age showed up as being older than the highest or the oldest person I could find in the state. There's a lot of reasons why that could occur. I just basically set a cutoff at age 106. So my regressions all went from age 18 to age 106. I downloaded the registration database. It comes in 4 enormous CSV files. I did some pre-processing in Microsoft Access, but most of the routine number crunching I did in Excel, so I'd have the data there to do the graphics you saw here. The polynomial regressions, and I'll talk about those in a little bit more detail in a moment. I used the statistical package R to do those, and I used those to compare residual errors in the polynomial regressions. And I did all of my decision making at a 95% confidence level. One of the questions is what order polynomial to use. My friend used 6th order. I have a suspicion for why he picked that, which is that that's the highest order. You can get an automatic trend line in Excel, so it's an easy way to do a bunch of quick scans of the data. That's certainly not the highest order polynomial Excel can do, but it requires a lot more work to get a good, rigorous regression outside of that trend line function. But I don't think we should kid ourselves about how meaningful these high-order polynomials are. Jan van Neumann said that with 4 parameters you could fit an elephant, with 5 you could make the elephant wiggle its trunk. So 6 parameters, that's a lot of parameters. I think that 8 parameters are better than 6. And the way I determined that was by doing successive regressions using R, and I just kept increasing the order of the polynomial until there was no statistically significant improvement in the F statistic as I compared the residual errors. So 8th order was the best. There was no justification to add parameters above there. I'll point out that you don't actually need to do this polynomial regression. You actually already have, if you've downloaded the data and done the pre-processing, the statewide turnout by age, and you can just use a table lookup, and that actually gives you better results, better correlations than the polynomial fit. So with that, thank you for hanging on to the bitter end here. I'd appreciate it if you would post any questions or reactions in the comments, but please keep them relevant to the specific points I'm making here. I basically plan to ignore any off-topic comments. If you'd like to see me walk through the R code or some of the other details, let me know in the comments and I'll make another video. And I'd like to thank a couple of people who I'm going to leave anonymous who looked at a previous version of this, and Brian Metz, who did a lot of work with my friend's regression analysis. And my results are very much in line with his findings. So with that, thanks again for paying attention. I'll look forward to your comments.